Hello fellow problem solvers. So there we're doing a problem from the International Math Olympiad shortlist from 2003, problem number G2. I suggest you try this nice, decent-ish geometry problem out for a minimum of 20 minutes. Ideally 45 to an hour and 15 minutes, not more than 2 hours. If you'd like to go along with us, give this a go for the next 10 minutes. And now let's begin. So what do we have here? We have 3 points that are on a line. They are fixed points, A, B, C. And then a circle that passes through A and C. Ka-boom, ba-da-ba-doom. There's the circle. The tangents at A and C meet at what point? Point P. And then PB intersects this circle at point Q. And now what do we have? We need to show that the angle bisector of AQC intersection AC, so where this angle intersects here, and this is point D, that this is independent of the circle. So as the circle grows and expands and shrinks, goes up and down, as P really moves up and down, and so does the circle, we need to show that, that this point D, the angle bisector, will remain the same. So now, with this in mind, I invite you to pause for 3 minutes and ask yourself, what is it that we have to prove? Looking at the problem forwards. Pause now. And the answer is, well, we need to prove that really D is constant, so that AD over DC is constant. So we need to prove that AQ over QC doesn't depend on the choice of the circle. Okay? So we need something around AQ over CQ. Okay, so we need this to be constant. Now that we figured this out, I invite you to pause for another few minutes and ask yourself, do we really need the circle, and how can we get rid of the circle? Pause now. And here's the answer to that. Well, let's say that these angles are alpha. Alpha, right? That's what angle condition is. We can define P like that. And then this is the angle X, X, and then this is the angle alpha minus X, alpha minus X. But you can imagine that we could define this. So we have ABC, right? We pick a point on the side bisector of AC, B, AC, there's B. This forms the angle alpha. And we need to pick the unique point on B, on PB, such that the angle, PA, the angle QAC is equal to QCP, right? There's a unique point such that this is true. And now we don't even have the circle. There's no more circle. We just have X, X, alpha minus X, alpha minus X, and we need to show that AQ over QC is independent, that we can really evaluate this just by using the lengths of AB and BC and AC, right? That is what we need to show. So the question is now, that's looking at the problem forwards, what do we really need? Do we really need the circle? And with this, here I gotta pause for a bit longer, because now here's alpha, this is 180 minus alpha. And I have to ask you, how are we going to do this? And you need to pause for now 10 to 15 minutes and ask yourself, what do I do here exactly? And the answer is, okay, it's difficult. It's difficult. We really need to show that AQ over QC is really equal to sine of X over sine of alpha minus X. This is thinking about this trigonometrically. Now we need to show that sine of this over sine of this is something that can be expressed in terms of AB over BC. And in fact, it's probably going to be AB over BC in some respect, given that if B was closer to C, this would be closer as well. So now with that in mind, how are we going to, how do we express this? This is not AB over BC isn't equal to AQ over QC, otherwise these angles would be equal, and that's just not true. And I mean, how do I actually go ahead and prove that that's not true? I mean, then these, like, it looks like it's not true. Let's just put it at that. It looks like that's not true. So how do we use now this fact? So sine of x, sine of alpha minus x. Well, one way to see it is like there are these angles here. Call this angle, what's it called? Z. And then because the whole is, this is 180 minus z minus 2 alpha. And then I have sine of x over sine of z. And I'm looking at it here because it will give me PQ twice, and then those will cancel out. So PQ is equal, this is equal to PQ over AQ. And then sine of, what's it called? Z plus 2 alpha, or sine of alpha minus x is equal to CQ over PQ. Now mind you, when I multiply these through, I'll get not this, but really the opposite. I won't get, like I'm not getting AQ over CQ, but rather when I multiply them, I'm getting CQ over AQ. So that's going to be a bit interesting. So now I have that sine of x over sine of alpha minus x times the sine of z plus 2 alpha over sine of z. This is equal to, when I multiply these through, the PQs cancel out, is equal to CQ over AQ. But now I know this thing is equal to AQ over CQ. So I have CQ over AQ squared, once I substitute this for this, is going to equal sine of z plus 2 alpha over sine of z. Okay? Now, can we, like, this is also a way for us to evaluate AQ over CQ. But now that I have sine of this over sine of this, I can bring it back to AB over BC. Because if I look at these two triangles, and I have alphas on this side, so that's a positive thing. So I'll get that sine of z over sine of alpha is equal to AB over BQ. Actually, is it, yeah, over BQ, over PQ, or no, P over PB, my bad. And then here, I'll get that sine of alpha over sine of alpha plus 2z, actually 2 alpha plus z, is equal to, so sine of alpha, again, PB over BC. And when I multiply them together, alphas cancel out, and I get sine of z over sine of z plus 2 alpha is equal to AB over BC. So now I have this quality. So what does this give me? Well, I have here really the opposite of this. So I have this thing is equal to, from here, it's equal to BC over BA. And this finishes up the problem because now we have shown that AQ over CQ squared is equal to BA over BC, or that AQ over CQ is equal to the square roots of AB over CB. And now this shows that when you intersect it here to this, like this angle bisector intersects at D, you'll have that AD over DC is going to be equal to this, which is a constant. So for two different Ds, it's on this segment. I mean, you can actually prove, like, if AD over CD is AD prime over CD prime, then when you add 1 on both sides, you'll get CD plus A. And this is just like technique at this point. You'll get CD plus AD up there, and CD plus AD will be AC over CD is equal to AC over CD prime. In other words, CD prime is CD. right? If both points are here, and this finishes up our problem. Now, if you came at this from the playlist on the Simidian lemma, you might be confused, like, wait, why aren't you using the Simidian point? Like, I thought this is what this is all about. And the answer is I didn't want to. It was harder to motivate the Simidian point, but we can motivate that lemma as well. The lemma is really that this, if you take the midpoint M of AC, that this angle right here is equal to this angle right here. That's what the lemma says. And now what happens when you take the angle bisector and it intersects at point D? We have BD over DM is BQ over MQ. Right? We have that also holds true about point D. And we can try to see like if something is interesting about D there. And for me, this is like, I know the lemma, and then I'm like looking at how I can get this point D. So I see that it's not immediately obvious how this can be used. Well, then maybe BD over DM, I have this over this is equal to this over this. Now we need this over this. And what is that equal to? Oh, actually, wait a second. So there's a lemma. Again, this is trigonometry, I believe, if I'll use that lemma. But there's a lemma, really, which is just an application of two sines. If you're a triangle ABC, beta, gamma, the midpoint M, then sine of this over the sine of this is equal to the sine of beta over the sine of gamma. So what does that mean here? Well, this means that, what's it called? If I take the midpoint M, I'm trying to calculate, I'm trying to calculate AQ over CQ, right? And on one hand, that is sine of X over sine of alpha minus X. But if I apply it to this lemma over here, that is also equal to the sine of at this angle over this angle. And so when I switch these around, it's going to equal the sine of this angle over the sine of this angle. Actually, it's going to equal. And when I take the M, it's equal to sine of this over sine of, let me write it down, sine of MQC over sine of the angle MQA, which is then equal to the sine of the angle BQA over sine of the angle BQC. And with that, I need to now calculate the sine of this over the sine of this, and I guess I would do the same thing as I did here. I would now go back to, so I have BQA, I'd look at this one and I'd look at this angle, their sines, that would give me this thing right here, and I think we would end up in the similar place where we started at. Yeah, I think we'd also end up that proving, like via the theorem of sines, that AB over BC, the square root of that is equal to AQ over CQ. But I would just like be another way to go about proving this. And this finishes up the problem. Like we would end up like this. And this is a problem where, you know, just like trigonometry proves to be useful. I'm curious if there's a synthetic solution, right? One that doesn't use trigonometry. Maybe one that only uses this lemma. And if you know one, please let me know in the comments below. And as always, thanks for problem solving.